Okay, so before we get into the notes for 1.3, we're going to start by talking about horizontal asymptotes. If you look at problems 5 through 7 on the actual notes, that's what we're going to work on as a warm-up. So just a little pre-calc review, reminders about horizontal asymptotes, stuff that you may want to write down if you have forgotten. If we are looking at a rational expression, the horizontal asymptotes relate to the degree of the numerator and the degree of the denominator. So if the degree of the numerator is smaller than the degree of the denominator, then you have a horizontal asymptote at y equals 0. So that would be something like x over x squared. That would give you a horizontal asymptote of y equals 0. Versus if the opposite of true is true, x squared over x, then there is no horizontal asymptote. And lastly, if they are equal, then what you're going to do is divide those coefficients. So if I have 2x over x, I'm going to have an asymptote at y equals 2. That's what I get when I divide those leading coefficients. So now go ahead, pause this video, go back and look at those 5, 6, 7. So those 3 problems, numbers 5, 6, and 7, and see if you can identify the horizontal asymptotes. Okay, so for number 5, we're taking in the numerator the square root of x squared minus 3x plus 1. Now remember, when we're identifying asymptotes, the only thing that matters is the leading term. So the only thing I care about in terms of asymptotes is my square root of x squared over my x. Well, that's the same thing as x squared to the power of 1/2 over x. If we multiply those, we're going to end up with x over x, which means that we have the same degree. And if you remember what we just said, if we have the same degree, then our asymptote is what we get when we divide the coefficients, which is just 1 divided by 1. So we have a horizontal asymptote at y equals 1. Similarly on number 2, and I just like to rewrite the leading terms with rational exponents instead of radicals, I'm going to end up with the same degree in the numerator as the denominator, so I'm going to divide those coefficients, which again is just going to give me y equals 1. If we look at 7, x to the third to the 1/3 is really just going to become x over 5x to the third. So the degree of the numerator is 1, the degree of the denominator is 3. That means that we have a horizontal asymptote at y equals 0. So you may need to go online, find a video, and brush up on those skills if they are lacking. But that idea is going to lead us into our lesson for today. So part of you should be thinking, why are we talking about horizontal asymptotes when we've been talking about limits? So if you look over here, I want you to think about what a horizontal asymptote is. It's looking at the behavior as x approaches infinity. It's saying that our function is never going to cross this dotted line, even as the x's continue to get bigger and bigger and bigger, or smaller and smaller and smaller, depending on the type of function. So 1.3 is all about infinite limits at infinity. So it should lend to that idea of an asymptote, looking at sort of the end behavior of a function. So the way you're going to see this, the limit as x approaches infinity or negative infinity, it could be either, of f of x is called a limit at infinity. Again, it's really similar to thinking about what is the end behavior of that function. It is possible that that limit exists, meaning that it is equal to some value. It is also possible that the limit does not exist. So this is going to connect to our warm-up in terms of thinking about what's happening with the highest degree, with the numerator and the denominator, and where is it growing faster, and the behavior of how it's growing. So there isn't a whole lot of work that you're going to show, just like there wasn't really work that we showed in the warm-ups, but we're going to keep these facts in mind. So what I mean by that is if the degree of the numerator is greater than the degree of the denominator, think about what's happening there. the top is going closer and closer and closer to infinity while the bottom is doing the same thing but at a slower rate. So what we're saying here is that the top is growing faster than the bottom, which means that the limit either does not exist, or you could say that it's plus or minus infinity depending on where the limit is happening. If the degree of the numerator is less than the degree of denominator, in terms of asymptotes, like we talked about in the warm-up, that's going to say that we have an asymptote at y equals 0, a horizontal one. Similarly, with this limit, that means that the limit is going to be equal to 0. Because what we're saying there is that the numerator is growing slower than the denominator. And that means that we're having something small over something that's getting big faster, which is approaching 0. And then lastly, if they're the same, just like with the warm-up, we're just going to simply divide the divide the leading coefficients, and that's going to give us the value of our limit. So on this first example, I'm going to show you sort of a factoring methodology to help you understand why this last fact of dividing the leading coefficients, why that works. After that, you really don't have to show that step. So if you look at this first example and you actually factor out the leading coefficient out of the numerator and the denominator, you're going to have x to the fifth times this quantity. And notice that as x goes to infinity or to negative infinity, all three of these terms are going to 0. So that they become less important in terms of determining the end behavior or determining the limit. Similarly, in the denominator, you're factoring out a 3x to the fifth. And notice if I distributed, I would get back to this original limit. But each of these is going to 0. So we really don't need to consider those factors. All we need to consider is what's happening as x goes to infinity of x to the fifth over 3x to the fifth. Well, as x goes to positive infinity and negative infinity, the x to the fifths are changing at exactly the same rate. So what is left? The only thing that really is significant here is the 3 in the denominator. So the limit as x approaches both positive and negative infinity, since the degree is the same, is going to be 1/3. So in reality, the only work I need to see is the little yellow work, but the rest of the work is helping you understand how and why this works. If you look at this next one, as x approaches positive and negative infinity, the degree of the numerator is greater than the degree of the denominator. Thinking about just the degree, the square root of 9x squared is giving me 3x over 5. Notice I'm not saying that those two things are equal. They're not, but in terms of the behavior that I care about, that's what I'm looking at. Now, since the degree of the numerator is greater than the degree of the denominator, this limit does not exist. Okay, if you look at the next few examples, you can go ahead and pause the video and see if you can find those limits if they exist, and also state the horizontal asymptotes of the function. If you look at number 1, we have 3x squared is dominating the behavior in the numerator, and x to the third is dominating the behavior in the denominator. So our degree of our numerator is less than the degree of our denominator, which means the bottom is growing faster, which means that this limit is going to be equal to 0, and the horizontal asymptote is going to be y equals 0. If you look at number 2, the terms we care the most about, the highest degree terms, 11x to the fifth over x to the fourth. The numerator is growing faster than the denominator, so that limit does not exist. It would also be acceptable if you think about what's happening. I'm plugging in negative values for x. So the denominator, since it's to an even power, is going to always be positive. The numerator, since I'm going to negative numbers, I'm going to negative infinity, the numerator is going to be getting more and more and more negative. So you could also say that this limit is equal to negative infinity. Then we're going to go ahead and look at number 3. Number 3, they are the same degree. If they are the same degree, then the limit is what we get when we divide their coefficients. That's 14 over 3 That is also going to be our horizontal asymptote. I didn't mention this, but there is no horizontal asymptote on number 2. And then lastly, number 4, again, we want to consider what's happening in the leading term. So let's first just think about what the leading term of this polynomial would be, or of this function would be. I have x squared, and eventually I'd be multiplying that by 2x. So that's really 2x to the third in the numerator and 5x to the third in the denominator. Notice, again, I'm not saying these are equal. I'm just looking at the leading term in order to analyze the behavior of the limit. So these are the same degree, which means they would divide out as x approaches infinity, or in this case, negative infinity, which means all that's left is the coefficient. So this limit would be equal to 2 over 5, and that horizontal asymptote would also be y equals 2 over 5. I wanted to show you what those look like graphically, which is a feature that does not work well with recording like this. So if you go to the slideshow in Google Classroom and you click on this link down here in the slideshow, it'll take you to each of those functions graphed, and you can see what's happening as x is approaching infinity or negative infinity. So we briefly touched on this on one of those examples, but here's what happens when we are and are not allowed to say if a limit is equal to infinity or to negative infinity, depending on the value. So that happens as long as both one-sided limits are approaching the same infinity value. So this still means that they don't exist, because infinity is not an exact number. We're not saying the limit is exactly this number. We're saying it doesn't exist, but we can be more specific in saying it doesn't exist because it's approaching infinity, or it doesn't exist because it's approaching negative infinity. The only way that that's true, again, is if both one-sided limits are approaching the same infinity. So if you look at these first two graphs, the first one, both of these around that vertical asymptote are approaching infinity, and both of them are approaching positive infinity. Similarly, on this example, they're both approaching negative infinity. So you could say that the limit as x approaches whatever this c value is on this dotted line, you could say that it is equal to infinity, and you could say that it does not exist. And most of the time those are interchangeable. It doesn't matter which one you say. That is not the case when they are approaching different infinities, positive versus negative. So here all you can do is say that the limit does not exist. You can't say that it's infinity or negative infinity. You can just say that it does not exist. So you can only conclude infinity or negative infinity if both sides, the left and the right sides, are approaching the same infinity. Okay, we're going to work through these last examples and see what we come up with. So if you think about the limit as x approaches 3, we can't use direct substitution because we would have 1 over 0. And that kind of brings up the whole issue. We have a vertical asymptote at x equals 3. So in order to say, right off, we can say that this limit does not exist. But if we want to check and see, could it be infinity or not, we need to look at the graph. This function, if graphed, is going to look something like this. You can type it into a graphing calculator to check if you want. There's a horizontal asymptote at y equals 0, which you can tell just from the function itself. So these are not approaching the same infinity. The left is approaching negative infinity, the right is approaching positive infinity. So this limit does not exist, and that's as specific as you can get. Thinking about number 9, as x approaches negative 2, the denominator is approaching 0. So let's think about graphically what this function looks like. We know there's going to be a vertical asymptote at x equals negative 2, and then the function actually on either side is approaching here. Thinking about that, if you just look at the denominator, every output is going to be positive in the denominator. So we actually can say that this limit does not exist, but we could be more specific and say that this limit is positive infinity. Number 10, you can simplify a factor of x minus 3 out, and that leaves you with this function. I'm not even going to sketch a graph of this function. It's pretty strange. It has a hole. It has 2 vertical asymptotes, so it has different pieces of the graph. The only piece of the graph that we actually care about is the piece that's happening at x equals -1. And if you look at the graph, you could use Desmos or your graphing calculator to graph this. You're going to see that the left side approaches negative infinity and the right side approaches positive infinity, which means that this limit simply does not exist. We can't say that it equals positive or negative infinity because it's not approaching the same infinity both from the left and the right. If you didn't have the ability to graph, what you could do is think about a number close to -1, both to the left and the right of -1, and plug that in and see what happens. You're going to get a negative number for one value and a positive number for the other, so it's clearly not approaching the same value of infinity. So that's an analytical way to approach number 10 if you didn't have a graphing calculator. Something important to note about 11 and 12 is that they are both asking you about a one-sided limit. I can tell because of the superscript. So the only thing that matters is what's happening to the right of 3. So the limit as x approaches 3 from the right. So we're looking at the behavior from the right. And so from the right, this limit is going to be positive infinity. And then number 12 is asking the same question from the left. That's going to be negative infinity. 13 is also a one-sided limit, so let's just think about the behavior of 2 minus x over x minus 5 squared, quantity squared, as we're approaching 5 from the right. So no matter what happens, if we're approaching 5 from above, so 5.1, 5.2, 5.0001, 2 minus whatever that number is going to be a negative number. Thinking about the bottom, no matter what happens, even as we get closer and closer and closer to 5, I have a positive number that I'm then squaring. That is going to be a positive number. So we know that this limit is going to be infinite because of that asymptote. And based on the signs we just calculated from the numerator and the denominator, we can say that this limit is going to be negative infinity, since a negative divided by a positive is also always going to be a negative. Again, this limit still does not exist, but being able to describe it as negative infinity is more specific and can be more useful depending on the circumstance. So recapping this lesson, you should understand how to find a limit as x approaches infinity or as x approaches negative infinity. And if a limit does not exist at a particular c value, you should be able to identify if that limit is positive or negative infinity, or if it simply does not exist. And that pretty much sums up 1.3.